Okay, today we are going to discuss about the interference and conditions of interference. That is conditions to obtain or sustain the interference, and then types of interference. That is constructive interference and then destructive interference. Okay. Thereafter, we are going to discuss about the Young's double slit experiment and its applications. Okay. Okay, fine. Now, firstly, we'll see the definition of the interference. Definition of the interference. Okay. The definition says that if two light waves superpose together such that at some point we'll have the maximum amplitude and we'll have the other point will have the minimum amplitude. That is, in the resulting wave, we'll have the maximum amplitude and the minimum amplitude. Okay. Suppose, let us consider I'm having a wave. Suppose, let us consider I am having a wave like this. And I'm having another wave like this. So I am considering this one as the first wave, having a displacement as y1, and this is my second wave having a displacement. Okay. Whenever these two superpose together, then the superposition of maximum amplitude of the first wave will superpose with the maximum amplitude of the second wave, such that in the resulting wave will have the maximum amplitude, right? This one, A max. Similarly, here, what happened? Maximum amplitude. Okay. Here I'm having that. Okay. Here. Here I'm having an amplitude here I'm having an amplitude A2, that is minus A2, and this one it is minus A1. Okay. Now at some point we'll have the, or this one it is 0 and here. So suppose at this point, there is a change in amplitude, and that we are calling it as minimum amplitude. The interference which is producing the maximum amplitude, we can call it as, okay, the interference which leads to the combination or superposition of maximum amplitudes can be called as constructive interference. Constructive interference. And the interference corresponding to the minimum amplitudes can be called as destructive interference. Destructive interference. Okay, now? Fine. Destructive interference. Now, first of all, we'll discuss about the conditions to obtain interference. Okay. Okay. Condition to obtain interference means the two light waves, okay, which are going to superpose must be coherent waves. That is, we are having a coherent source which are emitting these light waves. Okay. Coherent waves means these light waves will have same frequency, constant phase difference. Okay. Either same amplitude or different amplitude. Okay, na? Then only we'll have this interference will be possible, either constructive interference or destructive interference. Second one, it is the light rays or the light waves must be monochromatic. Okay, na? Manish?
Yes, sir.
Must be monochromatic. These are the conditions, okay, for the light waves to be superposed. Okay. Suppose if any of the condition is not satisfied, then we will not get interference. In order to obtain interference, we are having these two conditions. First one, it is the light rays must be emit from the coherent source only. And second one, it is the light waves must be monochromatic. Now, here, according to our definition, you can see the interference of maximum amplitude of the two waves can be called as constructive interference, right? Maximum amplitude. Okay. So we'll get the maximum amplitude. When the phase difference must be phi equal to 0 degrees or 360 degrees, right? Yesterday we discussed. Okay, na? So this leads to have the constructive interference. Similarly, minimum amplitude will get when phi is equal to 180 degrees, which we are calling it as destructive interference. Okay. Corresponding to this maximum amplitude, will have the intensity will also be maximum. And similarly, minimum amplitude means we'll have the minimum intensity. So I can say that for destructive interference, intensity will be minimum. Okay, na? Fine. Now, let me introduce a parameter or quantity called path difference. Which we can indicate with delta, like this. Okay, na? I'll share the notes, Manisha.
Okay, sir.
I will share the notes. Likewise, yesterday I'll share notes. Okay. Suppose, okay, let us consider I'm having an source. Okay. Here I'm having a source such that let us consider any optical instrument. Okay. Simply I will consider an prism. Okay. Such that this optical instrument should have the both reflection and refraction. Okay. Okay, fine. From this, let us consider I'm having a light ray. That is, it is moving in the form of a wave. Another light ray, here I'm having It is moving. Okay. Let us consider we are having the two light rays. Whenever these two light rays incident on the prism, it will undergo the property of reflection and refraction, right? After refraction, if I draw a normal, okay, let us consider this is the distance travel, and here it is. Okay, okay, fine. Let us consider this as AB, this as CD. Okay, now I will explain the path difference. Path difference, it is delta. I can write it as distance traveled by the light rays, okay, after reflection or after refraction. After refraction, distance traveled by the light ray is CD. And the first ray, it is AB, right? Okay, now, is it fine? Hello? Path difference means it is the difference in the distance traveled by the light rays after reflection or after refraction. If I consider it, instead of prism, we'll have the mirror. We'll have the mirror. Okay. In case of mirror means we can explain the path difference with the property of reflection. In other cases like lens, prism, or microscope or telescope, we can explain with respect to the refraction. So path difference, it is the difference in the distance traveled by the light rays or light waves after reflection or refraction can be called as path difference. Okay, na? Is it fine?
Okay, sir.
Okay, fine. Now let us consider I'm having a wave. Okay, let us consider that I'm having a wave. Like this. Suppose this point is O. Okay, here it is M. This is N. Okay, this is P. This one is Q, R, and then S. Okay, from O to Q, observe carefully, or otherwise M to R. O to Q or M to R. I can consider it is one cycle, right? So I can consider it as wavelength. I can consider it as wavelength. That's why we'll show like this lambda. Okay, now?
Yes, sir.
Okay, fine. Now tell me, for one complete cycle, what will be the phase difference?
So 0.
0 or 2 pi. So
Yes, sir.
for one complete cycle or one oscillation, one complete cycle, okay, phase difference is equal to 2 pi, right? Distance traveled by the light wave, I can say path difference is lambda. Can I say? Okay, na? Okay, fine. Now that means for a path difference of lambda, we are having an phase difference 2 pi. We are having phase difference 2 pi, right? Let us consider some angle That is when the phase difference is in between 0 to 2 pi. 0 to 2 pi. Okay. Now let us consider some phase angle phi. With respect to this phase angle, we'll have a path difference. Right? I'm considering some angle. Suppose let us consider from here to here, m to n, pi by 4. For pi by 4, it will have a corresponding path difference that I am considering as delta. For a path difference of delta, I want to find what is the phase difference. Okay, that is this I am considering it as phi. So by using the ratio and proportion, I can write as delta by lambda times 2 pi. Can I write? Okay, na?
Yes, sir.
So phi is equal to 2 pi by lambda times delta.
Yes,
That
sir.
is the relation between phase difference and path difference. Path difference, it is difference in the distance traveled by the light waves after reflection or refraction. You can consider either reflection or refraction. Okay. Okay, fine. Suppose let us consider an example. Let us consider an example. If path difference equal to lambda by 4, I can find phase difference. Okay, na? That is pi by 2.
Yes, sir.
Okay, na? Okay, fine. Now you can see that it is when phi equal to, okay, fine. That is, this is the relation between phase difference and path difference. For constructive interference occurs or happens with respect to the maximum amplitude. With respect to the maximum amplitude. In order to obtain maximum amplitude, what should be the value of phi?
So 0 or 2
Phi
pi.
will be 0 degrees or 360 degrees. So that means it is in the multiple of, okay, 2 pi times n. Okay, na? So when phi equal to 2n pi, I can write as 2 pi by lambda times delta. So condition to obtain the constructive interference will be delta equal to n lambda, where n will start from 1, 2, 3, and so on. That is where capital N, it is the set of natural numbers. Capital N belongs to the set of natural numbers. Okay, na? Okay, fine. So this is the condition. This is the condition to obtain the constructive interference. Delta equal to n lambda. Okay, and condition for the constructive interference, phase difference, it is phi equal to 2 pi n. Phi equal to 2 pi n. Okay. Okay, fine.
Okay, sir.
Next comes to the destructive interference. Destructive interference. By definition, we know that destructive interference happens with respect to the superposition of minimum amplitude of the two waves. Minimum amplitude of the two waves. So that is, in order to obtain the minimum amplitude, the phase difference must be equal to 180 degrees, right? Phase difference must be 180. Okay. Okay. 180, 540, etc. So in generally, I can write it as, okay, 2n minus 1 times pi. That is where n belongs to 1, 2, and then 3, and so on. Okay, right? Okay, now here that means 2n minus 1, it is my odd multiple. It is my odd multiple. Okay, I can also write with odd multiple means I can also write with as 2n plus 1 times pi. Can I write?
Yes, sir.
Whenever I am writing 2n plus 1 into pi, n will starts from 0, 1, 2, 3, and so on. Okay. In every case, we'll use 2n minus 1 into pi. Only in one of the case in diffraction, only we'll use 2n plus 1. So preferably use 2n minus 1. Preferably use 2n minus 1 only. Because here in 2n minus 1, suppose if it is third fringe, phase difference will be 2 into 3 minus 1. 2 into 3 minus 1. Here third means second one. N must be 2. 0, 1, 2. Na? That's why here it is just we'll have a confusion. Number third wave means if we are using 2n plus 1 notation means you need to write n equal to 2. Okay. Okay, fine. Suppose when phi is equal to 2n minus 1 times pi, what will be the path difference? Okay, since we know that the relation between phase difference and path difference is phi equal to 2 pi by lambda times delta. So 2n minus 1 times pi is equal to 2 pi by lambda times delta. 2 pi by lambda times delta. So delta equal to 2n minus 1 times lambda by 2. Right? That is the condition for the path difference to obtain the destructive interference or minimum amplitude or the minimum amplitude. Okay, na? Fine. And this is the condition for the phase difference to obtain destructive interference. Destructive
Okay, sir.
interference. Okay, fine. These are the conditions we got. Okay. Suppose if it is first minimum, that means n will be 1. N will be 1. So that is delta equal to lambda by 2. Okay. Second minimum means n is equal to 2. So that is delta equal to 3 lambda by 2. Okay. Fine. Now, see suppose let us consider here we are having an device called slit. That is, we are having an optical instrument, okay, in which we are having a small gap will be there. A small gap will be there. This instrument, we can call it as slit. This instrument, we are calling it as slit. And this small thing is there, na? This one, that we are calling it as aperture. We are calling an aperture. Okay. If you see, I think in some of the apartments, at the entrance door will have a small hole. Will have a small hole. Anytime have you seen?
No, sir.
In the entrance door will have a small hole at the middle, so that we can see the who came and who ring the bell, calling bell. Like that, at the doors will have a small circular hole will be there, so that we can able to see. That small circular hole can be called as aperture. Okay, and this entire instrument we can call as an slit. Okay, entire instrument we can call as an slit. Suppose let us consider I am having a slit. Okay, and here I'm having an source. Suppose this is coherent source. This is my coherent source. Okay, fine. Now this is the slit width. I can call as D. I can have the light rays will passes through the slit in this direction. Okay, and I can have the slit. I can have the light rays which are passing on the edge of the slit, right? Like this, on the edge of the slit. Okay, fine. Now here let us consider this is number 1, number 2, and number 3. 3 light rays are there. Okay, na? Fine. Okay, the light ray which is moving at the middle of the slit will goes undeviated. Will goes undeviated. Okay, this is undeviated. Light rays 1 and 3, it is deviated. Since the light rays incident on the edge of the slit will absorb some of the light, some of the energy of the light rays. Since the light rays 1 and 3 are incident on the edge of the slit, so the light rays, the slit will absorb some of the energy of the light rays. Due to that, intensity will be decreased. Intensity will be decreased. Let us consider this is my screen, right? The first light ray, let us consider that the first light ray will get, okay, it is refracted. Let us consider this one as S1 and here it is S2. Okay, and this point as P and this point as Q. That means here the light ray will get refracted in both the directions. Okay, na? Is it fine?
Yes, sir.
Okay. Similarly, here I'll have that from S2 also, the light ray will get diffracted, right? Okay. Now, after the refraction or after diffraction, these two light rays will meet, that means at superimposed, and forms an resulting wave at point P and Q. At point P and Q. Okay, na? First,
Yes, sir.
light ray will get diffracted. And then it is superposed. Due to the superposition, here we are having at P and Q. At P and Q, we are having an interference pattern is observed. Interference pattern is observed. Okay. Okay. Now, here I want to find the what is the path difference. What is the path difference? Here the light ray is moved from S1 to P and S2 to P, right? Hello,
Yes, sir.
right? So path difference I can write as S2P minus S1P. Can I write?
Yes, sir. We can write that.
Okay, na? That is the definition. Na? Our definition S2P minus S1P. S2P minus S1P. Okay, fine. So that means this is my path difference. With respect to Q means I can say that path difference will be S1Q minus S2Q. Okay, is it fine?
Yes, sir.
Okay, fine. Based on this one minute. Now see the one example problem. Here I kept the 3 examples. Can you see the first question?
Yes, sir.
See, two coherent sources emit light waves, okay, which superimposed at a point where these can be expressed as, we are having the two light waves, okay, and observe carefully. In the first wave, amplitude is E0. Second wave, amplitude is 2E0, right? Angular frequency is same. We are having a phase difference where E1 and E2, are the electric field strengths of the 2 points. And if I is the intensity of the wave expressed by field strength E1, find the resultant intensity. I need to find the resultant intensity. Okay, na? Is it fine? Okay, na?
Yes, sir.
Okay. Now, by definition, I can say that intensity means energy absorbed or energy emitted per unit area and per unit time, right? Okay. Here I'm indicating area with S because A means we indicated with amplitude. Na? That's why. Okay. So energy, whenever it is energy, I can write it as energy means it is in the form of work done. That is nothing but force times displacement. Okay, na? Force means due to a charged particle, I can write the electrical force as Q times E. Okay. Is it fine? Okay, na? That means I can say that intensity is directly proportional to the electric field strength. Can I say? And I know that intensity is directly proportional to the square of the amplitude. Square of the amplitude. Since resultant intensity, I'm having the equation formula resultant intensity
Sir, I1 plus I2 plus 2 under root
times
I1
under root
I2
I1 I2
cos
cos.
phi.
Now see the equation. In the first wave, in the first one, we are having an electric field amplitude as E naught. So I can say that I1 is equal to K times E naught square. Okay, na? K times E naught square. And similarly, I2 can I write as K times 2 E naught whole square. Okay, na?
Yes, sir.
Okay, fine. Now, phase difference between the two waves.
Sir.
Phase difference between the two waves,
Sir.
right? So phase difference between the two waves will be pi by 4 minus of, I am finding phase difference of the first wave with respect to second wave. That is nothing but pi by 2. I am finding phase difference of first wave with respect to second wave. Right? Okay, na? Okay. Suppose now you can see here I can say phi 1 equal to plus pi by 4. Phi 2 equal to minus pi by 4. Here why I am finding phi 1 2 only means you can also find phi 2 1 also. What will be the value of phi 2 1?
Sir, negative pi by 2.
Negative pi by 2. In our formula, cos phi, cos of negative pi by 2. Cos of minus theta, again cos theta only, na?
Yes, sir.
Okay. Even if you find phi 1 2 or phi 2 1, anything will be the same. Anything will be the same. So phi 1 2, that is pi by 2. So I'll substitute here. So resultant intensity IR equal to I1 I got as K times E naught square, K times E naught square plus I2 K times 4 E naught square plus it is cos pi by 2, that is 0. So I can say that resultant intensity will be 5K E naught square. Okay, na? That is nothing but resultant intensity will be 5 times the intensity of the first wave. Okay, na?
Yes, sir.
Fine. Is it fine?
Yes, sir.
Okay. Okay, fine.
Sir,
Ah,
sir, in given equation,
ah,
E1 is equal to E naught sine omega t plus pi by 4. So E
ah.
naught is as amplitude.
Yeah, E naught will be the amplitude, na?
Okay, sir.
Because we are having the equation, na? Y equal to
Yes, sir.
A into sine omega t plus 5, omega t minus kx plus 5,
Yes, sir.
this one. Even there is a chapter called electromagnetic wave. We'll have the electric field equation. E equal
Sir,
to E naught
yes, not
times
sine omega.
that one, and alternating current also.
Yes, sir, in alternating current also.
Uh, okay, fine. That is our first question. Next, second question. You can see 3 questions are there. We'll discuss. We are having the 2 sources, S1 and S2. Okay, 2 sources, S1 and S2, emitting light of wavelength, 600 nanometer, are placed at a distance 10 power minus 2 centimeter apart. A detector can be moved on the line S1P, which is perpendicular to S2. That means, let me draw the diagram. We are having here S1 and here it is S2. Okay. Okay, fine. This, it is the distance D. And a detector can be moved on the line. Oh, S2 pin. Suppose this is S2 and this one it is S1. Suppose here we are having a detector at point P, which is perpendicular to S1 and S2. Okay, fine. This is okay, fine. And then which is perpendicular to S1 and S2. What would be the minimum and maximum path difference at the detector as it moves along the line S1P? As it moves along the line S1P, okay, S1 to P, what is the minimum and maximum path difference? And thereafter, I need to find locate the position of farthest minimum detected. Okay, now let us consider this detector means it acts as a screen. Can I say? It acts as a screen. It is at a distance
Yes.
D. It is at a distance D. Okay. Fine. So, given that lambda equal to 600 nanometer, 600 nanometer. Okay, na? Hello?
Yes, sir.
Okay, na? Fine. Now, I need to find the minimum and maximum path difference. Okay? Okay. Delta maximum means it will be n lambda, right? And delta minimum, it will be 2n minus 1 times lambda by 2. Can I say? Okay. In this one, minimum means I will consider the first order. So maximum it will be, okay, that is this one, distance. Okay. Minimum it is delta minimum must be lambda by 2. Okay, na? Okay. Delta maximum must be lambda. Since I know that lambda equal to 600 nanometer. Hello.
Yes, sir.
That means this detector, whenever this detector, okay, is at S1, this is the maximum value. This detector is moving from S1 to P now, right? When the detector is at S1, when detector is at S1, then delta will be maximum. Okay. That is the first point. And second point, as detector moves along S1P, then delta will be minimum. Can I say? Delta will be minimum. So delta max is nothing but is equal to D. That is 10 power minus 2 centimeter. Okay, na? And delta minimum will be lambda by 2. That is 600 into 10 power minus 9 by 2. Approx it is 300 nanometer. Okay, na?
Yes, sir.
Okay, na? Is it fine? See, that is our first bit. Minimum and maximum path difference at the detector as it moves along the line S1P. Next, position of the farthest minima detected. Position of the farthest minima. That means path difference delta equal to. Here path difference I can measure as the detector moves from S1 to P. Path difference will be S2P minus S1P. Can I write? As the detector moves, P is my detector, it is moving towards P now. So path difference I can write
Yes,
as
sir.
S2P minus S1P. They are asking to find the farthest minima. So that is 2n minus 1 into lambda by 2. That is S2P minus S1P is equal to lambda by 2. Can I write? Can I write? Okay, na?
Sir, it can be, can we not put n is equal to 2 or any other number than
No.
1?
No. Why? Because here they are asking to find locate the position of farthest minima detected. Okay, that means the minimum value which is detected by this detector, which is
Okay, sir. Now I got.
okay, because D is equal to 10 power minus 2 centimeter and lambda equal to 600 nanometers. That is approximately 6 into 10 power minus 7 meter. Otherwise, I can say 6 into 10 power minus 5 centimeters. Okay, that means always in order to travel the wavelength of light, it must be very, very less than the distance between the sources. So S2P, you can see this one, S2P means this value. That is under root capital D square plus small d square. S1P means it is capital D. It is capital D. So under root capital D square plus small d square minus capital D is equal to lambda by 2. Okay, now upon solving, we'll get as capital D square plus small d square equal to capital D plus lambda by 2 whole square. Right? If we expand it, we'll get as okay, na? Right?
Yes, sir.
Okay. So we know lambda and small d. I can find capital D.
So then can we neglect lambda square, as lambda square will be so less value?
Okay. We can find the distance now. If we substitute the values, we can find. Okay. Like this. Next one. Is it fine? This one? This question?
Yes, sir.
See once. If it is fine means we'll go to next question. Okay. Okay, now fine. Can I go to next question?
Sir, sir, is answer coming as capital D is equal to 1/60
1 over?
meter. 1/60 meters.
No. 1 minute. D square equal to lambda square by 4 plus lambda capital D. Okay. Then this one it is 10 power minus 4 centimeters. Lambda it is 6 into 10 power minus 5 whole square by 4 plus 6 into 10 power minus 5 into capital D. So capital D equal to, sorry, 10 power minus 4 equal to 9 into 10 power minus 10 plus 6 into 10 power minus 5D, right? Okay, na?
Sir, then can we neglect 9 raised or minus 10, as it will be a very small number compared
9
to
into 10 power minus 6 plus plus 6 into 10 power minus 1. So capital D equal to 1 minus 9 into 10 power minus 6 upon 0.6. Okay, na?
Sir, in centimeters.
Centimeters. So D is equal to 1 minus 3, 4, 5, 6 by 0.6.
Sir, can we neglect?
Actually, we can use the binomial expansion. Previously only we should use it. 0.1, 2, 3, 4, 5. Something around 1.66 centimeters. 1.66 centimeters. Okay. This is the
Yes,
calculation.
sir, I am getting this answer too.
You got?
Sir, same answer.
1.66. Okay. That is at a distance of 1.66 centimeter. Okay. We are having the farthest minimum. Okay. Fine. Now, next comes to the next question. You can see two coherent sources, S1 and S2, vibrating in phase, emit light of wavelength lambda. The separation between the sources is 2 lambda. That is previously we considered as D, small d. Consider the line
Yes, sir.
passing through S2 and perpendicular to S1 and S2. Find the position of farthest and nearest minima. Okay. Hello.
Yes, sir.
So here what we can consider it as farthest minima. As it moves away, wavelength will be decreases. That means I can write it as, okay, I can write it as for farthest minima. Farthest minima. I can consider delta must be equal to, okay, farthest minima, na? 3 lambda by 2. And nearest one, it will be lambda by 2. Right?
Sir, farthest one will be lambda by 2.
Here, 2 point sources, S1 and S2, vibrating in phase, emit of wavelength, lambda, and distance between the sources is 2 lambda. Yeah, farthest minima will be lambda by 2, and this one will be 3 lambda by 2. Okay?
Yes, sir, as we done in previous
Ah.
question.
Fine. So here it is. Here it is. Firstly, okay, that is path difference. I can write it as S1P minus S2P because we are having This is S1, S2, and here it is P. This one they gave it as 2 lambda. Okay. This value I will consider as D. This value I'll consider as D. Okay, fine. Now this must be equal to 3 lambda by 2. 3 lambda by 2. That is under root of 4 lambda square plus D square minus D is equal to 3 lambda by 2. Okay, now. So 4 lambda square plus D square equal to D plus 3 lambda by 2 whole square. Is it fine?
Yes, sir.
Okay. Upon solving, we'll get as 4 lambda square plus D square equal to D square plus 9 lambda square by 4 plus D into 3 lambda. D times 3 lambda equal to 4 lambda square minus 9 lambda square by 4. That is 7 lambda square by 4. So D is equal to 7 by 12 lambda. Okay, na? Now, for the farthest minima, for farthest minima, delta must be equal to lambda by 2. Okay. So again, under root 4 lambda square plus D square minus D is equal to lambda by 2. Okay, na? Upon solving, we'll get 4 lambda square plus D square equal to D plus lambda by 2 whole square. So 4 lambda square equal to lambda square by 4 plus D into lambda. So D is equal to 16 minus 1, 15. 15 lambda by 4. Right? Okay, na?
Yes, sir.
Okay. On this, that is before going the YDSC, they will ask to find the path difference. They will give the sources and a detector or screen. Okay. Like these questions are there. Okay, na?
Okay, sir.
Fine. Now let us come to
Sir,
yes.
sir, in this third question, sir, the minimum nearest minima is lambda is equal to 3 lambda by 2. As it maximum we can go is part difference we can go as 2 lambda, the distance between two sources. If we coincide S2 and P.
See, this is nearest.
Yes, sir, this is nearest and other one is farthest.
Otherwise, 7 by 12 means I can write approximately 0.58 lambda.
Yes, sir.
This is approximately 3.75.
Yes, sir. 3.75.
Right now. By obtaining the distances, after obtaining distances, you can decide which is the far and which is the nearer.
Okay, sir.
right? Okay, fine. Next, okay, up to where we came, up to here we came, na? Interference, and then types are completed. And then types are completed. Next, comes to the next topic, it is Young's double slit experiment. Young's double slit experiment. Okay. Okay, fine. In short, we can write it as YDSE. YDSE. Suppose let us consider I am having a coherent source. I am having a coherent source. Here we are having that double slit. Double slit. This here I'm having aperture now. This I can consider it as S1. Here I can consider this one as S1. And here it is S2. So distance between the slits, this total distance, we are considering it as D. Okay, fine. Now here it is that from the slits at a distance D, we are having a screen, or you can consider it as a photographic plate. We are having a screen, or we can consider it as a photographic plate. Okay, fine. Let us consider this distance as capital D. Now, from here, the light rays are incident on the slits S1 and S2. Initially, the light ray will get diffracted. Light ray will get diffracted. Thereafter, light ray will be superimposed, just like before. Here we discussed now, like this. Whenever the light ray is incident on any optical instrument, then the path of the light ray will be changes. This property can be called as diffraction. This property can be called as diffraction. Okay, na? Fine. Okay. Now, here this is coherent source. This is, I am considering it as coherent source. Okay. Okay, fine. Now, whenever the light rays are incident, let us consider I am having the light rays are incident. Okay, na? Are you following, Manish? Manish? Okay. Let us consider this is the light ray 1 and then 2. The central one, it is light ray number 3. Light ray number 3. Whenever the light ray passes in between the slits, it will go undeviated. It will go undeviated ray. So whatever the intensity is there before incident of the slit, suppose it is I. After passing through slit also will have the same intensity, I only. Okay. For light rays 1 and 2, if we are having an intensity I1, after passing through the slit, the intensity will be decreases. It will be less than I1. Okay, na? Fine. Is it fine? Manish?
Yes, sir.
Fine. Okay. Whenever the light ray is incident on the slit S1, the light ray will get diffracted. The light ray will get diffracted. Okay. Okay. Here. Similarly, at point from S2 also. From S2. After diffracted, the light rays will get superimposed, which results in the formation of interference. Which results in the formation of the interference. Okay. Let us consider this point as P and this point as Q. Okay. Fine. So that if I draw a perpendicular here and similarly here, such that this distance will be d by 2, that is this one, and this distance is also d by 2. Okay, now this point I am considering as M and this point I am considering as N. Is it fine? The
Yes, sir.
superposition of the waves, with the superposition of the waves, will have the minimum amplitude and maximum amplitude. Center one, it is the maximum intensity. So the superposition of the waves, this we are calling it as fringes. This we are calling it as fringes. Okay. Okay. And these fringes will be either it will be straight or it will be circular, or it will be in the circular. Okay. Or it will be in the circular. Okay, fine. So central one, since it is having maximum intensity, we can call it as bright fringe. Bright fringe. With respect to the central fringe, in the above and bottom, we'll have the dark fringes will be formed. Alternatively, bright and dark. This is first dark and then second bright, second dark. Similarly, down also. First dark, second bright, second dark. Like this. From central fringe to the point P. Point P, I am considering it as nth bright fringe. Nth bright fringe. Okay, na? Such that from the central fringe to the nth bright fringe, it is having an distance or fringe width as yn. Fringe width as yn. Okay, na? Is it fine, Manish?
Yes, sir.
Similarly, from central fringe to the down, this distance it is yn. Here also we are having the nth bright fringe. Nth bright fringe. Okay, fine. Now, here I need to find the relation between this yn. Yn can be called as distance between the fringes. Distance between the fringes. So it can be called as fringe width. It can be called as fringe width. Okay. This fringe width can also be indicated with beta. In some textbooks, they will write with either with the letter beta or with the letter yn. Okay, na? Is it fine?
Okay, sir.
Okay. This. Okay. Now we need to obtain a relation for this fringe width, yn or beta. That is our aim. First, what I'm doing it is, I'll find the path difference, delta. Can you tell me what will be the value of delta?
Sir,
Ah,
S2P minus S1P.
very good. S2P minus S1P. So I can write as S2P minus S1P. Okay. In order to find S2P and S1P, firstly, I am considering the triangle S1MP. See, S1MP, this triangle. That is S2P in the triangle S1MP. S1P whole square is equal to S1M whole square plus MP square. Right? See, in the triangle,
Yes, sir. Using Pythagoras theorem.
by using Pythagoras theorem, okay, S1M. What will be the value of S1M? Means nothing but capital D. Capital D na. So it is capital D. Now MP square. Now observe carefully. CP I can write as CM plus MP. CP, it is nothing but Yn. CM, that is nothing but D by 2. So MP is Yn minus D by 2. Okay, na? Is it fine? Okay, na? Is it fine? So S1P square is equal to D square plus Yn minus D by 2 whole square. Similarly, okay, na? Hello?
Yes, sir. Yes, sir.
Next triangle S2NP. See, S2NP. Again, I will apply Pythagoras theorem. In the triangle S2NP, that is S2P square equal to S2N square plus NP square. That is, what is the value of S2N? See the diagram.
Sir, capital D.
Capital D only now. NP. What is the value of NP? NP means I can write NC plus CP. Can I write?
Yes, sir.
NC
Sir, twice
D by
one.
2 plus Yn.
Yes, sir.
Okay, na?
Yes, sir.
Okay. So that is capital D square plus Yn plus D by 2 square. That is nothing but S2P square. Now, I need to get the value of S2P minus S1P. See here. So in order to get that value, S2P square minus S1P square, I am finding. Okay. That is nothing but D square plus yn plus d by 2 whole square minus d square plus yn minus d by 2 whole square. Okay, na? Is it fine?
Sir, it's come out to be 2 dyn.
So in the left hand side, I will write it as S2P minus S1P times S2P plus S1P is equal to, what we will get, it is 2 times 2yn into small d by 2, right? Okay. So S2P minus S1P is equal to 2yn small d by S2P plus S1P. Okay, na? Is it fine?
Yes, sir.
Okay. Now I need to get the value of S2P minus S1P. This is nothing but S2P minus S1P is nothing but path difference. Right? Okay.
Yes, sir.
Now see here from the diagram, in this triangle S1MP, I can say S1M equal to D. Here it is making an angle theta. Let us consider this angle as theta. So cos theta is equal to D by S1P. Can I write? Hello?
Yes, sir.
That is S1P equal to D by cos theta.
Yes, sir. Yes, sir.
So the minimum and maximum value of cos theta is, minimum value is -1, maximum value is +1.
Yes, sir.
Since distance cannot be negative, so the maximum value of S1P and S2P will be 2 times capital D. Right?
Yes, sir.
So I can write delta equal to yn times small d by capital D. So yn is equal to capital D by small d times delta. Okay, na? Okay, na? Fine. For constructive interference, or to obtain the bright fringe, delta must be equal to n lambda. We know na. So fringe width that is equal to capital D by small d times n lambda. Okay. For destructive interference, that is to obtain the dark fringe, delta must be equal to 2n minus 1 times lambda by 2, right? So fringe width will be capital D by small d times 2n minus 1 times lambda by 2. Can I say? Okay, now. Hello, Manish,
Yes, sir. Yes, sir.
right now. For destructive interference, we are having the fringe width as capital D by small d times 2n minus 1 into lambda by 2. Okay. And for constructive interference, we are having the fringe width as capital D by small d times n lambda. Okay, na? Fine.
Yes, sir.
Okay. Based on this, we are having the applications. Based on this, we are having the applications. Okay. Based on this, we are having applications. Once today, go through this one, Young's double slit experiment theory, only the theory. Tomorrow, we'll see the applications of this Young's double slit experiment. Okay.
Okay, sir.
Okay, na? Okay. Tomorrow, we'll see the applications of this Young's double slit experiment. Thereafter, we'll see the interference in the thin films. Okay. Fine.
Okay.
Okay, na? Okay, we'll meet in the next class.